I'd like to take a look at a few graphical examples of limits of composite functions. If you remember, one of the properties of limits with composite functions is that we can evaluate a limit of a composite function by essentially looking at, the value of f at the limit, as in this example, x approaches 2 of g of x. And if we do that, in this example here, we can see that g of x is approaching 4. It's approaching 4 from both sides. So this should be the value of f of 4. But we have a problem over here. F of 4 is not continuous. And so if you remember, that property only holds if f is continuous at 4. In this case, it's not. So we don't get to use that. And what I said in that video is we need to analyze what's going on with our one-sided limits. So I'm gonna just look at both of the one-sided limits individually, and then remember a two-sided limit, which is the one where we don't have that exponent there. A two-sided limit exists if both of the one-sided limits are the same. So let's start by looking at what happens as x approaches 2. But with values of 2, or values of x that are slightly smaller than 2, so approaching 2 from the left. So if we look at the inner function first, so we're plugging 2 in for x, so into g of x, what we get here is 4, same thing we talked about before, but we're gonna look at this a little bit more closely. Not only is it approaching 4, but it's approaching 4 from below. So the values that we get along the y-axis over here are getting closer to 4, but they're values that are a little bit smaller than 4. So essentially, kind of what I'm thinking in my head is we're going to be taking this limit here of f of values a little bit less than 4. So what we can actually do is write it as a new limit. And now x isn't approaching 2 from the left, but it's approaching 4 from the left. And I just want to clarify, it's not 4 from the left because it was 2 from the left. It's 4 from the left, okay, because we're looking at values of x that are a little bit smaller than 4. Because g was approaching 4, but it was a little bit smaller. So because of that, then we go over here to the graph of f, and as we approach 4 from the left, we are approaching a value of 5. So one of our one-sided limits, the left-sided limit of this composite function, is going to be 5. If we look at what's going on from the right, so x approaches 2 from the right side of f of g of x, when we plug in values that are a little bit bigger than 2 into g, we're approaching 4 again, but this time we're approaching 4, but we've got values that are a little bit above 4. So we're coming from above instead of below. So that would be the same thing as looking at this limit. So we're approaching 4 from above, and we look at what happens with f of x as we approach 4 from above, and we get 2. So since these two one-sided limits don't match up, then we're going to say that this does not exist. Now, it might be tempting after the first example to say, okay, well, when this happens and f isn't continuous, then it's always not going to exist. Well, let's change it up a little bit. So the only difference here is the graph of g looks a little bit different. So let's analyze one-sided limits again. So x is approaching 2 from the left of f of g of x. And as we put values into g that are a little bit smaller than 2, then we're going to get values that are a little bit smaller than 4. So this is going to be the same as the limit as x approaches 4 from the left of f of x. Okay, so again, g is approaching 4 from the left, so that turns it into this limit here. And then as we approach 4 from the left, this hasn't changed from the last problem, we get 5. Here's what's going to be different though. As we approach 2 from the right, on G, okay, so we're plugging it into the inner function, we're approaching 4, but this time it's 4 from below. So notice the graph of G is below 4 on the y-axis as we approach that value from the right. So this is actually going to be the same limit. So we're approaching 4 from the left on f of x, which is also 5. So this time those two limits do match up. And so what ends up happening is we get a value for this limit. We get a value of 5. So just because f wasn't continuous at x equals 4, that doesn't mean that we're going to get a limit that does not exist. A couple more examples I want to look at. This is a composite function. It's kind of an interesting one because it's a composite function where it's f composed with f, which is, there's nothing wrong with doing that. So if we look at what happens here with our one-sided limits, limit as x approaches 2 from the left first of f of x. So when we take the two values of 2 and plug it into the inner function, from the left we're going to be approaching 2, but we're approaching 2, I'm sorry, we're not approaching 2, we're approaching 4. But we're approaching 4 from below. So this is going to be the same as the limit as x approaches 4 from the left, okay, because we got values that are a little bit smaller than 4 of f of x. So this is the outer f now. It's this one here. And as we approach 4 from the left on the graph of f, we're going to be approaching a value of 5. The right-handed limit, so we're coming from the right side this time, f of x. So as we approach 2 from the right side, we're going to be approaching a value of 4 again, but this time we're approaching 4 from a slightly higher value. So x is going to be a little bit bigger than 4 because f of x is a little bit bigger than 4 of f of x. And when we approach from a little bit bigger than 4, we're going to be approaching a y value of 2. So these two one-sided limits don't match up, and this limit does not exist. Okay, you may have noticed that the graph of f and the graph of g in the functions that I used earlier are really similar to each other. So when I just composed f with f, it's essentially the same thing as what we would get if we had two separate graphs of f in the previous problems. One more example just to kind of complete this example set. We're going to look at one-sided limits in this example. The graph of f changed a little bit here. So the difference is we're approaching 2 from the left. F of x. So as we approach 2 from the left on the x-axis, we're approaching 4 from the left on the f of x axis. So the values that we're plugging in there are approaching 4, but slightly smaller than 4. And then as we approach 4 from the left, we're going to be getting 3. And then our right-sided limit, so as we approach 2 from the right, this time as x approaches 2 from the right, we're still approaching 4 from below. So this right here is approaching 4 from below. And that's the same as we had above, which is going to give us 3. So this limit does exist because both of the one-sided limits are the same, and that's going to be 3. I do want to just talk about one more thing here. This can be a little confusing when I say x is approaching 2 at first, and then I switch to saying x is approaching 4. So with problems like this, what a lot of people will like to do is just throw in another variable. So we might say the limit, and I'm just going to do one of them here. So the limit as x approaches 2 of f of x. So what we could do is as x approaches 2 from the left, we said that's approaching 4 from the left. So we might say the variable, I don't know, c is approaching 4 from the left. So f of x is approaching 4 from the left. So we'll just throw that variable c in there and say the limit as c approaches 4 from the left of f of, and we're calling the c in here now, so f of c. That's equivalent to what I did before. I just replaced the x's with a dummy variable. So that just it eliminates that confusion with using x in both of them, even though we're really representing two different things with it.